In this video, we are going to talk about how to troubleshoot EMC radiated emissions problems, how to troubleshoot them in your own lab. And this can be super useful if, for example, you have a product which is failing this EMC radiated emissions test, or it can be super useful if you are designing a product which will need to go through this test, but you are not sure if it's going to fail or pass. Because if you can measure this in your own lab, then it can save you a lot of money. I'm not an expert for EMC, so I had a call with Min. I recorded this call, and that's what you will see in this video. As an example, in this video, we are going to use this LED lamp, which has huge EMC radiated emissions problem. You can see it here on this spectrum analyzer. And I really like the call with Min because you will see the complete process of troubleshooting this product. And initially, there will be this like, we are trying to fix it and nothing works, and then suddenly we will find the problem, and like this, everything will start working. If you don't have much time, I created chapters. You will find them in the description, so you can quickly jump to specific topic what you are interested about. But this is not very long video, so if you watch it like in double speed, it will be like half an hour, and you will learn a lot of things which I hope you will find interesting and useful. Okay, that's everything for introduction, and we are going to start our call with turning on the LED lamp and checking the radiated emissions by this spectrum analyzer. Watch this purple line, and when the LED lamp will be on, you will see a lot of noise or many peaks on this purple line. So here is my call with Min. Wow. And you really can buy this in a shop or on internet.
Yes. Let's just quickly have a look at the setup we just demonstrated. It's very easy. We have a lamp, and the lamp is, as I said, it's a mains product. So it's plugged into the socket. So in EU, we're talking about 230 volts. In the US, 110 volts. And the setup we have a little antenna. This antenna is pointing towards the lamp.
Is it important how you put the antenna, if horizontally or vertically?
Yes, it is important. Normally, you would put it horizontal and then vertical. But because we are trying to fix something, if we measure it in a vertical direction, as we show here, as long as we can fix it always using the vertical, then it's adequate, basically.
So but maybe initially you try both directions and you will see which one is more noisy, and then that's the one which you will use?
Yes, that's a very good method. Because as I said, this is a very simple pre-compliance test setup, which I hope lots of people can reproduce this in their office or in their lab. But if you send this to a accredited EMC lab, they will have 3-meter distance with big, antenna, and then they will do it properly. Yeah.
Mm-hmm. Can you buy these antennas, or where did you get the antenna?
Yes. So this particular antenna I use, I'll show you in the next slides. Yeah. So this is the simple setup I just mentioned. You have the lamp put in here, and then I have a 1-meter distance, and then you can see I marked everything using tapes, because this is quite important. Radiated emission can be different with slightly different setup. So make sure that your setup always be very consistent. And this little antenna I use is from an RF engineer. He had a small company, and he designed this PCB-based antenna. But in reality, you can use any type of antenna you can find. For example, remember the little radio station we had. That antenna is called rod antenna. You can use that antenna and it's the same. You will pick up noise straight away.
Because the radio picks up the noise too.
Exactly. Normally, different antennas will have different signal reception range. For example, this antenna is supposed to have very good reception between 400 megahertz and 1 gigahertz. But as you can see later on, for this noise, which is predominantly between 10 megahertz and 300 megahertz, this antenna still can receive the signals. So the point is, if you can have any sort of antenna, even like a TV antenna, you pick up the noise and then you make some change and then you see some 10 dB, 20 dB reduction, then you know you basically reduce the noise.
But ideally you would like to have wide range antenna, so you can, I think in EMC test house they even change the antennas, correct?
Exactly.
So you can do measurements for one range, and then when you are happy with the results you can change the antenna and check if there is nothing in different frequency range.
Yes. So you're right. The types of antenna can be many. You have the log periodic, so like this shape, and then you have the biconical one, you have the home one, you have rod antenna. Many types of antenna work from different frequencies, as we said.
Where is the 1 meter between? Where exactly it is?
So this one is from this point, as you can see, this this green tape I had, to this point is about 1 meter.
So these are just like marks which you have like reference points.
Exactly. You can put in 1.5 meter or but yeah, roughly normally for pre-compliance EMC tests, put into 1 meter is a good distance.
Okay. And I'm just, this is maybe a weird question, but I remember I was talking about this with someone else. Usually the distance in the test house is so large because we would like to measure the far field. So it means we really don't want to go too close because the near field may not be exactly what we would like to measure. Or is there some kind of relationship between like near field and far field, or what is your opinion about this?
Yes, you're absolutely right. The idea of testing equipment on a product using 3 meter or 10 meter distance is exactly the reason, as you said, you don't want the near field to affect your results. So basically what we're saying is when, it's very similar to lots of videos you did with other people talking about energy traveled in space. And when you have energy, electromagnetic energy travel in space, it's from the far field point of view, the electrical energy and magnetic energy should be the same. But when you get too close to a product, it could be predominantly electric field or it could be magnetic field dominant. So you don't want to, for radiated emission point of view, you don't want to get too close. That's why I said normally 1 meter is just on the boundary. You don't want to put it too close. 1 meter, and then there are some equations that can, adjust your results to say 3 meter value. But it's not in the scope of today's discussion.
Okay, but I wanted to mention this so everyone knows that maybe they don't want to measure 20 centimeters from the board because they may get maybe not the results what they are looking for.
That's exactly, we should mention this. Yes, this is a very good point.
Okay. So I see spectrum analyzer. Okay. Tech box EMC view software. Okay.
It's just a software that we use for scanning, and and it's a very simple test setup. As I said, if you have a spectrum analyzer and some form of antennas, then you can easily troubleshoot, basically.
Okay, I would like to go back to the video because I'm not sure if we pointed out the noise.
Okay. Yeah, sure. Okay. Yeah. So as you can see, before I play the video, you can see that I already had the test set up, and you can see on the let me just zoom in. The on the spectrum analyzer, I have two channels basically. The first channel is a yellow trace, and the yellow trace is I do a scan basically without plugging in the LED light. So the LED light was not plugged in. It
So
is where it
this is what you
but it's
call
not
ambient, and these are basically
ambient.
all the noises picked up by the antenna from, I don't know, like Wi-Fi or something. I don't know what are the
Exactly,
peaks
exactly.
there.
Yes, you get it right. The peaks here, probably one of the peaks is actually there's a very, I think it's about 12 or 14 kilometers away. There's a big transmission broadcasting station for BBC. So you always have this signals. And yeah, this is the ambient. And once we plug in the product and we power the LED, then you will see all the noise going up. Yeah, this is just basically the radiated emission we measured using the antennas here.
Okay, so yeah. Can we play it again so everyone can see it?
Yeah, sure.
Okay, now we can see the purple, and that's the noise what the lamp is making.
Yes.
Okay.
Yes. You can see the spectrum was pushing high, and then also the radio station has been heavily affected. Basically, the music you listen to has all the noise. Yeah.
Okay. So what is the next step? We know there is something wrong with the lamp. What we are going to do next?
Yes. So before we do a full-scale operation on this product, you know, like often you send a product. Let's say this lamp is our design. We designed this lamp, and we send it to a EMC test lab, and then they test it and say, oh, no, it's not good. And what normally the EMC lab engineers, test engineers, would always give you some advice. These advice probably not from the design perspective, but they are quite practical. So for example, in this case, they will probably tell you, okay, let's put some ferrite on the cable, or let's shorten the cable. So let's just have a look at what this means, okay?
Okay.
Normally, radiation occurs because there's some cable structure, and cable can radiate quite easily. So as a general advice, normally people will say, let's try to shorten the cable and to see if we can bring down the noise. So shorten the cable normally is what they suggest in the first step.
Okay, and that's what we are going to try now?
Yes, exactly.
Okay.
So the result you see in this video, I also basically save it. So here's save the results. You can see on this side. As you can see, when we shorten the cable, we bring down the noise. If you look at this point, from here, 87 to 67, more than 20 dB. But you see the noise only is brought down from the frequency from, so here is 10 megahertz, 20, 30, 40. So from 40 megahertz to maybe 16 hertz, we had some noise reduction by shorting the cable.
And this is because the original 1.5 meter is good antenna for these frequencies?
Good guess. Good. Yes. So I put in here. So exactly as you just said, let's go to this page. So in this page, I basically put in more information here. The electronic circuit is located in a very little PCB on the socket or plug. And then it has a long cable, as I said, it's about 1.9 meter long.
Okay.
And then the lamp is basically LED diodes.
Mm-hmm.
So if you work out a cable length of 1.9 meters long, and then often a very strong resonance point is a quarter wave length. So assuming the speed of light is 3 to the 10 power of 8 meter per second, using the equation V equals lambda multiplied by F, and you can work out at a quarter wavelength at which frequency it's resonance very strongly. So in this case, we have 1.9 meters and a quarter wavelength is 0.5 meters, and then we calculated at which frequency it resonates very strongly, which is 40 megahertz. So that's why when we shorten the cable length, the frequency in 40 megahertz range brought down by 20 dB.
Mm-hmm.
Yes.
Was it 40 megahertz? Wasn't it a little bit higher?
It's starting from 40, so you can look at here. So this is 10, 20, 30, 40. Yeah, you can see 40.
Okay.
Yes, yes. Yeah, actually, this picture here. Yeah, 10, 20, 30, 40. Yeah, so from 40, you can see very, very big reduction.
And why is it quarter of the length? Why not? I think many people may wonder why it's not half.
Yeah, you can have half wavelength radiates very strongly, or quarter length wavelength radiates very strongly. As I put in on this very simple diagram here. So,
I guess half is for like dipole, no?
Yes, yes. So if you have a noise source, let's say sit in the middle, say in this case, and then you have cable going both directions, and then that cable length is half wave. But most of the time we find you have a product like here, and then you only have one cable, and that cable is a quarter wavelength basically.
Okay, I understand. Okay, we can go back.
But the idea is doesn't have to be a quarter wavelength or half wavelength. Cable at any distance can radiate. It's just at a quarter wavelength, at that frequency, 40 megahertz in this case, it radiates the strongest. But other frequency also radiates using the same cable, basically.
I guess also the multipliers of these frequencies will be radiating very well.
Yeah, when it comes to radiation, and particularly antenna theory, we can talk a whole book of this thick talking about the things we talk. Yeah, it's a very, very complicated science of physics. Yeah, lots of science behind it. Yeah.
Okay, we can go back.
Yeah. Okay, so the first thing we just tried is we tried to shorten the cable length, and we saw the effect, and we get a little bit understanding of, okay, the cable radiates. And then and the second thing, again, often engineers will find in an EMC test lab is they will say, oh, if a cable radiates, let's put some ferrite on the cable. Yeah, we know from the little tests we just did, we noticed that from 10 megahertz to 300 megahertz, we saw lots of noise. So when you choose a ferrite, it's not randomly, you shouldn't randomly choose a ferrite. You should choose a ferrite that has a lot of impedance in this frequency range. I think that's more important. Okay. So in this case, we chose a ferrite, as you can see, from 100 megahertz to 500 megahertz. We have very good impedance, 534 ohms. So we pick up this ferrite, and then let's see what happens.
So you place it close to the adapter?
Yes, I put it close to the adapter, yes. Because I already got a feeling that the noise source comes from that side. But I will show you the details later. Yeah. So let's have a look at the comparison results. Okay.
And if you would place it, okay, if the source is the adapter, and if you would place the ferrite far away, then it would not have as good effect as if you place it closer. So this could be also a way to find out what exactly is making the problems.
Yes, actually, you raised a very, very good question. Because sometimes not only say you put the ferrite in the wrong place, as you said, you don't know where the noise source is, and then you put it far away from the noise source. And sometimes what people found is actually they put the ferrite and then the noise increased. Yeah, the noise increased and it's getting even worse. And this is not unusual. This is what happens. And the simple explanation for that is because noise travels. And then if the ferrite is put too far away, sometimes it can reflect it back. Really depends on the frequency. There are many papers talking about it. I think in some particular case where you have two systems connected by a cable, and one system is working at one frequency, the other system working at double that frequency, then it is very tricky to put where to put the ferrite in the cable. I can't remember from the top of my head, but I remember if you put it in the wrong place, you actually see the noise increase. Yes. So.
But generally, when you place it further from the source, you will not get as good results if you place it close to the source.
Yes, because at the time when you put it too far away, the energy has already leaked into the space, basically.
Okay, so let's have a look what happened.
So here, as you can see here, we have the purple line is the original scan, okay, where without any methods, without any approach. Then the blue one here is when we shorten the cable. We already knew from 40 megahertz upwards we have some reduction. And then if you look at the green trace, you can see it's actually starting from I think 10 megahertz. Yeah, from 10 megahertz onwards to 100 megahertz.
How do you know it's 10 megahertz is the first one where it's...
So because this is a logarithmic plotting, so I stopped at 1 gigahertz. So I know this is 100 megahertz.
Okay.
And this is 10 megahertz.
Okay.
This is 1 megahertz. Yeah.
Okay.
So yeah. So so basically, we know that both methods work. But the idea is not really to put a big ferrite and shorten the cable, because imagine if we are developing this lamp, our boss probably wouldn't allow us to say, oh, you design a lamp with this long cable, or you design a lamp, but you tell the customer that you have to buy a ferrite. So yeah, so I think the next step for us is to look inside, what's inside, and can we fix the problem inside, okay? But I prepare some slides basically to explain what caused the radiation, okay? So again, it's very similar to the discussion we had last time. We're talking about common mode current and differential mode current. And as you can see here, most of the radiation happens when you have common mode current in the energy traveling path. So in this diagram, you can see that if I had common mode current traveling on the cable, and then you can see the current will form a loop, and then this loop basically is how radiation happens.
Common mode current is the current which flows kind of outside of our system, and the differential mode current, it flows in the system and in the connection to the system.
Yes.
Okay.
Yes, exactly. And basically, we talked about energy traveled in space, many times. So basically, we're saying that same example, but if we forget about current, it's really this area that is a loop, between the cables and the ground, or any metal structure, you have a loop, and that loop can radiate. We will come to these slides later on with details, but this slide basically is more detailed because I put the circuits into the drawing as well. Basically, what we're saying is common mode current travels through all the parasitics. If you have a transformer, you have parasitics, capacitance, and then the product itself will have some parasitic capacitance to the earth, and so current will always flow. Will flow using the least impedance path, and as long as we have this common mode current path, we will have radiation basically. But we will come back to these circuits later on in details when we dig into the product. Okay. So the next step really is to open up the product and then see what's inside and can we fix the problem inside.
So we are going to have a closer look at the lamp, and so how it is connected. I can see we were talking about this. So there is LED directly in the lamp, then there is long cable connected to adapter, and the adapter is connected to the main. So basically the LED is powered with DC low voltage, correct, from the adapter?
Yes. So I don't know, what's the LED lamp this particular case is about until I open it up. So this is how, when I opened the little black socket or plug, basically open it, and I had a look, and I was like, okay, so this is how they made. So basically, the whole circuit, as you can see here, is a very small, tiny PCB, and its own job is basically changing the AC voltage into a DC voltage. It's like this. It's a flyback switch mode power supply. Basically, you have the AC in, you have a rectifier, you have a DC link capacitor, and then you have a flyback transformer, which is essentially two inductors. And then you have a diode and a capacitor, and then here is the LED. And the cable really is just 1.9 meter long cable, but only carry DC voltage, low voltage DC. Yeah.
Okay. I see you have the picture operation principle of flyback converter.
Yes. So just in case some people are not familiar with flyback switch mode power supply, you can visit. I just picked up Texas Instrument. They have this very nice explanation, very simple one, so you can understand it.
So this adapter is changing the 230 volts to 12 volts, and this is how it looks inside. Okay.
Yes, but before they change into 12 volts, the first thing is they rectify it, so AC becomes DC, and DC is about 400 volts, high voltage. And then through the flyback circuits to lower voltage. Yeah.
Okay, and when they make it DC, then there is this special IC which makes from the DC some kind of switching voltage which goes through the transformer, correct?
Yes. Okay. So IC is just like a switch, basically. It's what we call isolated DC-DC converter. Like the buck converter we talked last time is non-isolated, and this one is isolated.
Because it's using transformer.
Yeah, you use the transformer for isolation purposes.
Okay.
Yeah, because sometimes you're dealing with AC is dangerous, and then normally they put isolated power supply. Yeah.
Okay.
Yeah. And yeah, so here is another test setup I used for troubleshooting radiated emission. And it's a very useful one because the problem is, the antenna setup we had is nice, but it's taking space. And every time you make some change, you have to make sure that the antenna always stay, and it's just not efficient to solve radiated emission problems. One of the efficient ways of solving radiated emission is to use something called a TEM cell, as I show here. So this one basically is, you can treat it as a very small scale, like a chamber, because then you can put your PCB basically inside, and then you do a scan, and then you find where the problem is, and then you can quickly get the PCB out, work on the same bench, and put it in, and then do another scan. So very quick troubleshooting tools.
But then is not this working with the near field radiation?
Yes, that's a good question. I'm sure it will pick up some near field, but the way it works is more suitable for troubleshooting radiated emissions. Yes.
So
because
probably if you fix this field in this small TEM cell, then it will also fix the big radiation, correct?
Yes. Yes.
Okay. And you have, how is it connected? The cable is connected. So
because it's a good question, because because we know that the original product, the AC cable, is very, very short because it has the plug and then long DC cable. And so I extended the AC cables by another 10 centimeters, simply because I can then put the PCB in the TEM cell. So you can see the plug is here, but I get the PCB out, and I extended it by 10 centimeters. Yeah.
Okay, I understand.
I think, I think we should mention this. Otherwise, this is not clear, because people will think, oh, you still have the plug here, but this plug is nothing. It's just AC lines. So the PCB is now sitting in here.
How this TEM cell looks inside when it is open? It is just metal, or?
It's a metal. It's two metal on top and bottom, and in the middle they have some PCB structure, and basically it's a transmission line. Basically, it's a transmission line that can pick up noise.
Oh, okay. So on one side there is termination or something, and on the other side you are connecting the spectrum analyzer.
Yes, exactly. Same way as it works as a transmission line. You have a 50 ohm termination. Yes, standard 50 ohm termination, and then the output is connecting to the spectrum analyzer. That's it. Yes.
Okay. So now we are going to confirm our theory that a lot of problem is caused by this power supply.
Yes. So,
so
again,
what are the results?
Again, first thing is we need to do a benchmark. So this is a benchmark test with the TEM cell results. So if you look at the problem, is again from 10 megahertz to maybe 300 megahertz, and it's at this time is 47 dB microvolts. Okay, so that's the benchmark level. We're aiming to bring this down, hopefully by 30 dB. That's our goal. Okay, yeah.
Why there are three different graphs? Orientation 1, 2, and 3.
Oh, okay. Yeah, this one basically again is something very similar to what we discussed before. For EMC testing, always make sure that you test different orientation. It's like an antenna, as we discussed. You have to test horizontal and vertical. So put things in TEM cell, because the way it works, you also want to triple check, this direction, and this direction, making sure that, as you put it, always pick up the worst case and then fix on the worst case. Yeah. Same idea, basically.
Okay, but the results are very similar, I can see on the graph.
Yes, the results are very similar. So at least from what I understand is, if the orientation doesn't make any difference, then probably it's because the cable radiation, because the cable, regardless where you put, it always radiates.
Okay.
Yeah. So
okay, so now we know that there are some problems on the PCB,
Yes.
and we would like to try to fix something.
That's right.
So what is going to be the first thing what we are going to try? Capacitors.
Yes, capacitors, my favorites. um, yes, I think from last time when we discussed the conducting emission, we already discussed many aspects of capacitors. So the principle is again very similar. It's the DC link capacitor is very important for switch mode power supply because it is the main energy source. And if you want to have less radiated problems and less conductive problems, always make sure that your DC link is good. So in this case, there are a few problems with this design. First is I think their capacitor's value is very small, okay? And you can see from this PCB, you can see the electrolytic capacitor is bended, yeah? So it's not really sits on top of the PCB, it's bended. And the reason for bended is because they want to pack everything into the small space. Yeah, but this is one of the problems I've seen in many other cases, is when you bend a capacitor, this bending, you can see, this is a long leads, and this will introduce extra inductance. So this is not good exercise. But sometimes engineers have no choice, because the height of the product is defined already by product engineers, and then you can't have otherwise the capacitor will be too tall, so you have to bend it. So but that's an introduction of some parasitic inductance, let's say.
I can see on the other picture you.
I put it on, yes, I put it straight, yeah. And I chose a larger one. So I changed the 4.7 microfarads, and then I changed into 10 microfarads, okay? So that's the first thing we did. And this is the improvement we made. You can see, yeah. So original cap is the yellow trace, and the purple trace you have about less than 10 dB improvement from 10 megahertz, or maybe less than 10 megahertz. You can see, yeah. And
okay,
then,
so there is little improvement, but not like what we would need.
Yes, but this product, we know that is the emission level is so high. So what we want to do is every step we bring down maybe 10 dB. So apply 5 steps, we get 50 dB. Basically, that's the idea.
Okay,
yeah.
I understand.
But you see, yeah, it's about 10 dB, I would say, 10 dB reduction. Okay, that's a good news. Okay, then the next step, is again trying to optimize the DC link a little bit better. So in this case, we changed the capacitance value, but it's still an electrolytic capacitor. And the next, I wanted to use some low impedance film capacitors. So I tried to put a 10 nanofarad capacitor in the DC link, yeah, as I draw here. And the idea is the same. Basically, you want to make your DC link capacitance a low impedance path, basically. And alternatively, because it's an X-type capacitor, it can also work on the AC side. You can put the same capacitor between the AC lines. That's also many products do this. They put the capacitor in between the AC, trying to provide some low impedance path. But in this case, I put the capacitor in DC, I put the capacitor in AC. They make things worse, as you can see here. They make things worse. So what we're saying is, we tried 2 methods, which in theory should work, but actually in reality, it makes things worse, okay? And why? So I think the next question probably, why it didn't work, You said making the DC link low impedance, it should work, but why it doesn't work? I think, again, this topic, you probably have already had a discussion with many other people in the past, but it's worth see it really how in reality it works. Is the X-type capacitor we choose is a 10 nanofarad capacitor. So you can see here is 33 nanofarad, here is 6.2 nanofarad. So the resonance point of this capacitor is somewhere here, okay, somewhere here. But because the layout of this PCB is terrible, which we'll see later on, which means the location I put these capacitors is not ideal. So when I put it there, I already introduced some inductance in the system. And when you put inductance, okay, so this is a simulation I did. I have a 12 nanofarad capacitor, let's say, but I introduced another 10 nanohenry inductance.
20.
So before it's 10, and then I added another 10, gives you 20. Yeah, and this is the result, as you can see. So this is 10, the dashed line here is 10 nanohenry originally, but this red solid line is 10 plus 10, and the other 10 is basically the parasitic inductors we talked about.
Okay, what does it mean?
What does it mean? It means you think yourself, okay, I look at this dashed line, I think, oh, you know, at 15 megahertz, I should have very low impedance. Yeah, you see the resonance point, and you see, oh, it's very low, should work. But because of the extra inductance we bring in the system, this is the reality. It's not low anymore. You look at the impedance here and the impedance here, you can see a 10 times difference. So I think that's a very good point for anyone to take, is you spend lots of time looking at the data sheet of a capacitor, but then you put in a circuit, but the circuit actually introduced more inductance than you thought.
So you think you picked up capacitor for, I don't know, 15 megahertz, but once you connect it to your circuit, because of the leads to the circuit, it actually may not work for 15 megahertz, but for something lower. And in 15 megahertz, it can be even worse, because for 15 megahertz, instead of placing their capacitor, you place their inductor.
Exactly. Yeah, that's the point we'll try to make.
Okay.
So that's basically, we tried all the methods of capacitor, but because of the layout, we cannot change the layout of this small PCB, so we are limited basically. But we know that the 10 microfarad electrolytic capacitor helps. That's the first step. Okay. And the second step is to shield the transformer. Okay. So as you can see here, I made a small shield and I put it on top of the transformer, and the shield, as I demonstrated here, needs to be bonded or grounded, as some people say, to lowest impedance path. Because in this system, there's no real low impedance path because of the layout is so bad. So we can only choose a relatively low impedance path, which is the negative VDC. So that's how I
how did you make this shield?
So this shield, you can make this shield very easily. You can use copper tape, you know. But in this case, I have something from Worth Electronics, as you can see. They sell this little shield sheet, and it's with all this little square, and then you can easily bend them to any shape you want. So I use it.
I never seen anything like this.
Yeah, it's a very useful shielding sheet.
So
yeah, you can see
you cut the shape what you need, you bend it, and then you use the copper tape to put everything together.
Yes, that's how I did it. Yes. Yeah.
And you can solder on the copper tape, or you can solder on the shield.
yeah, you sold. I soldered a very tiny wire from between the shield and the minus VDC.
Okay,
basically.
so you can solder on the shield.
Yes, you can.
Okay.
Yeah. Okay.
Is it expensive?
I would say this shield,
Yeah.
I think is not expensive. I think it's less than £10 for a big sheet. Yeah.
Okay.
And yeah, I would say this method 90% works, but in our case, it doesn't work. Okay. I think this is the interesting part. It doesn't work, but we'll talk about why. We'll talk. Yeah. So
and we will
the
fix
next
it.
step,
That's important to say.
Yes, we'll fix it. Yeah. Yeah, I think one of the great tips from Keith Armstrong, you recently did the interview he gave, is he said, if you make change, step-by-step change on some product, and you see one step change doesn't help, second stage doesn't help, third stage doesn't help. He said, as long as they're not making things worse, you shouldn't get away with them. Leave them there. Okay. So as you can see, now we're in step 3. So step 2 doesn't work, but I still have the shield. So I still have the shield. And next thing I'm doing is I'm adding some Y-capacitor. And the Y-capacitor works very effectively for common mode noise, as I demonstrate here. We know that the common mode current travels on both lines. So if you have common mode current going through your live and neutral, and then you put 2 Y-capacitor, and Y-capacitor, again, in this case, also provides a low impedance path. So they provide the low impedance path, and then your common mode current should be going back, should be returning via these Y-capacitors. And this is a very effective way of making a filter. So I put 2 Y-capacitors in the system like it is here. But again, no improvement. Yeah, no improvement. This is getting more interesting. And another thing we tried is we said, okay, lots of the methods we tried is on the high voltage side. Yeah, you look at all the high voltage side. We haven't tried anything on the low voltage side. So I put some ceramic capacitors, which again, supposed to work really well in the frequency range we're interested. So 2 capacitors, one works well between 1 megahertz and 10. The other works well around 100 megahertz. I put it on the low voltage side, no improvement. Okay, so step 4, we're still stuck. Okay. So as you can see, all the results we put in here, the purple is still our original scan, but then all the rest is just stay there, didn't make any improvement.
Maybe even a little bit worse.
Yeah, even a little bit worse. Okay. And I think that's one of the advice I want to give to all engineers. When you have problems like this, stay calm, drink some tea, maybe sleep, come back the following day, and then restart. Never get frustrated. Okay, so I basically stopped, and then I come back later. I said, okay, maybe we should, we look at the circuit and we think, oh yeah, it's a flyback switch mode power supply, but we didn't go into the details. So this time we went to the details, and
because
this is
you knew there is probably something really wrong with the circuit itself.
Mm-hmm. Indeed. So this time I really studied the whole PCB component by component, and I marked all the components here, and I draw the circuit diagram basically as the PCB layout. And here is what we found. It is the IC, this little IC has 7 pins, and basically I found a 7-pin device somewhere on the internet, and I think it's very similar to this. So I basically draw what they had. And you can see here the HV pin, basically these are the switch pin to this transformer. Then the VDD, of course, getting some voltage through this potential divider. And they have the feedback pin, but in this case, they never use. And what's strange is they have a C3 capacitor, basically connecting the VDD pin to the secondary side, the low voltage side diode. And this C3, in my opinion, is a wrong design, and it should never be there for many reasons. So that's the first sign I saw on this schematic, and I think something wrong with this design basically.
So in the left bottom corner there is the proper circle.
This one is one. This circuit is the one I found on the internet, and I think the chip is similar to the chip in this case, because you can see even on their data sheet they have the LED lights on. So I think it's a very low cost solution they use all the time.
And there is no capacitor between VD and okay, I see. It's basically I think this is what I draw based on this PCB, and I think that's how it is basically. I'll show you a proper one, then you will be amazed. Okay. So this is a demo board from ST Electronics. I found it online, and you can see the quality components they use. Did you see that they have a few capacitors? 1, 2, 3, 4, a few capacitors, and then you can see this is the transformer. And if you look into details, I'll zoom in. Did you see this thing here? It's what we call a belly band shield. So it's a shield on the transformer basically. Same as we try to apply. So they have a shield on the transformer, and they have this. I think this must be an X cap as well, or maybe a MOV. I can't see from this angle. And then they have a common mode choke, as you can see. All good quality stuff. And then if you look at their schematics, and then you will see, wow, look. On the low voltage side, they have LCC filter. On the high voltage side, they have capacitor, common mode choke. This C1 is the X cap. I was using very similar techniques, and then you can see their chip is much more complicated than the one we just saw. So you know that for these low cost solutions, they took everything else out basically. So that's the challenge. They removed component and say still works. Remove component.
Yes,
still works.
Always works. Yes. I'm pretty sure that's how they did it. So basically, as I said, now this time I studied the.
If we go back, I see they connected capacitor between the on the transformer, but it is in different place.
Yes, this capacitor, as you will see later on, is very important. It's very important. I will show you. So that's a good spot. So basically, this is a summary we put on this slide. We're telling, the layout is horrible. It's horrible, right? I can't describe how bad the layout is. It's just terrible, and it's not safe, right? That's why I said, be aware when you buy these cheap LEDs. Is even the high voltage design is not safe, right? Be aware, and basically there's no snubber circuit, no feedback. The whole design is really just functional. It's as long as I see voltage, then they're happy basically. Okay. So we said, okay, this C3 we discussed before is strange. So I basically moved that C3. And I think that C3 is already broken. It's just connected there. And then you can see, without doing anything, I just removed C3, you can see we have some improvement again, okay? Again, I think it's about 10 dB, yeah, maybe 5 to 10 dB, you can see the comparison. And at this point is a good sign. And I think, okay, at least now we're seeing improvements again. Okay. So so basically, yeah, we have, you know, we did lots of steps in before, but we didn't see any improvement. But now I found this C3, so I said, okay, you know what, let's make this point as our new starting point. And we try to bring down the noise from this point. The yellow trace is the ambient, and the purple trace is the new starting point without C3. So then we can have much better comparison. Because
so did you change also some settings in spectrum analyzer or in the connection, or you remove something?
Yes, I put all the change here. So you can see now, the previous one we measured up to 300 megahertz, but this time I measured up to 1 gigahertz again. And I might have changed the preamplifier or the attenuator in the spectrum analyzer as well. So I marked them, so now you can have a better look. Yeah. So the idea is really, as you said, you know, initially, if I don't apply any attenuator to my spectrum analyzer, it will go above the limit line and it's beeping and could potentially damage my. Yeah. So now we're in a stage that I can, you know, get rid of some of the attenuator. So now it's much better. Yeah, it's a good spot. Yeah, good spot here. Yeah. Okay. Okay. So now we call this the new step 2, because as we said, the step 2, 3, 4 should work, but it didn't work. Okay. So now let's call this the new step 2. As you spotted already, in the design, people often put a Y-class capacitor.
I have a question. I'm sorry for interrupting. So you removed all the previous changes?
So in these changes, I had, no, yes, you're right. I removed all the changes except
and we are starting again, basically.
Yes, except the low voltage capacitors. Remember, we also put some low voltage ceramic capacitors on the low voltage side, and we didn't see any change.
Okay.
So I didn't change these because, you know, I knew they are probably not doing any bad or probably not doing anything good, but I'll leave this.
Okay.
There,
and I see there is also 10 microfarad capacitor on the input.
Yes. Yeah. Sorry. Yeah, I should have marked here. This is still the 10 microfarad capacitor, as you can see here. So the only change is just the capacitor. Let's say we're changing to 10 microfarads. Okay. And yeah. So what we did first is I put a Y2 capacitor, which is 1 nanofarad, between the primary side and the secondary side ground.
So that's exactly the capacitor what we could see in the big schematic.
Yes, yes. As
they
you
also
can see
have
here.
2.2
they put
nanofarad.
2.2 nanofarads. I put 1 nanofarad. I also have 2.2, and I believe if I put 2.2, it will even better, be even better. Okay, but there's a point here I just want to mention. It's not like you can put very large capacitors. You know, we know 1 nanofarad is good, 2.2 is better, but I can't put 10, let's say. And the reason is because if you put too much capacitance between the two sides, the leakage current going through will be too big, and it's lethal. So standards basically define that you shouldn't put too large capacitance between the two to prevent leakage current. That's from safety point of view. So that's very important.
Why did you choose this capacitor as the major or one of the changes what we would like to try?
Because when I had a look at the PCB, you know, the first thing we saw is that the layout is terrible, which means they don't have a good solid ground plane. And which means if I measure the common mode voltage between this point and this point is going to be huge common mode voltage. And that's the main noise source of the whole thing. The problem is the huge common mode voltage between this point and this point. So naturally, the first step, I'm thinking is I put a Y capacitor here, and I can make that common mode voltage become less. And that's why I chose this method. In fact, I measured the common mode voltage, and you can see it's really bad. Yeah. I have the measurement video if you want to see it. Yeah. And it's pretty obvious that the common mode voltage is very high.
And if we place there the capacitor, then we kind of make short circuit for these high frequencies, and then the voltage will be same on the cables.
Yes. You are already jumping ahead. So basically, you understand everything. So that's exactly what we're going to see. So this is the result, right?
This is the result from what?
So this is the result. So the purple line is, again, we said this is the new starting point. That's the point we removed C3. And now we are putting a Y capacitor, 1 nanofarad Y capacitor between the primary side and the secondary side. And you can see it's a clear 10 dB reduction from very low frequency all the way up to high frequency. So this change is major change, across a wide frequency range, and it's 10 dB at least. Yeah. Okay.
So why this helped?
Yeah. Look, I had this slides. Why this? Why? Yes. As you already you already understand it. Yeah, it's really just to bring down the voltage difference from RF radio frequency point of view. Yeah, and I use a analogy here. Basically, we're saying that the previous tests, previous steps we did, why it didn't help is simply because we didn't fix the big pipe. Imagine you've got a leakage problem in this pipe. First thing you want to do is fix the big pipe, because that's the main source. So what we did just now, we put a Y capacitor here, is like when we fix a problem, we fix the big pipe of the system. So from this point, if we bring back all the methods we use, like shielding the transformer, putting Y capacitor, we should see step-by-step change now.
Okay, I understand. So because there was this huge noise, we could not really see any other improvements.
Yes.
And
basically,
this huge noise was caused by incorrect connection of the capacitor, because the original capacitor probably should be placed on the ground instead of the power. Yes,
and I don't know. I think they didn't even intend to put a Y capacitor, because the capacitor needs to be Y class rated. As you can see, it's a big disc ceramic capacitor like this. It's a Y class, because then you fail in a safe way. But they use a ceramic surface mounted capacitor. So I simply don't get it why they did that design. So yeah.
Okay, so can we explain a little bit more about this? So what happened? I explain it, but I would like to hear you to explain what happened when you place this capacitor there.
Yeah, so to understand it, I think you need to understand the common mode voltage. And in this case, the common mode voltage is this point, which is your primary side 0 volts point, and then this point, which is your low voltage 0 volts. And if you measure the voltage difference between this point and this point, you will see a big voltage jump between these 2 points. And particularly for radio frequency range, that's causing the problem. That's the RF voltage. So if you put a capacitor between these 2 points, and capacitor works with frequency, so when your frequency increases, the impedance drops. So basically, it's making sure that this point and this point, they are potential from RF point of view is more or less the same. So you don't have a voltage noise source between the two sides meaning primary side and secondary side. So you don't drive any emissions up. Yeah.
So basically, this 1.9 meter cable suddenly will have some kind of ground, but before it was not really ground.
Yes, I think this is a good understanding of it. Before, that cable is
Antenna.
Is an antenna, and the noise source is because there's really this big voltage difference between here. But now you have a capacitance, and then you basically reduce that noise source. So what we are saying is, actually this is one of the most important thing in the EMC world is if you solve the problem at the noise source, it's much easier. It's much easier. As you can see, if we don't solve this problem at this point, regardless, we put the shield, we put filters, it doesn't help, isn't it? So solving the problem at the noise source is always the best.
Okay, so we can go to the next slide.
Yeah. So next step is we are bringing the shield back. We tried the shield before and we didn't see any difference. So now let's try the same methods, exactly the same method, put the shield on, bonded it, and then see what happens. And this is what happens. So
wow, that's big difference.
Yeah, that's a big difference. Yeah, again, another 10 dB, from this blue trace is where we had the Y-cap fitted, and now we put the shield in, then you can see the green trace. So now another 10 dB, I would say, and it's quite effective, again, across a wide frequency range. And as I said, that's what we expect, actually. We expect the shield will work, but initially we didn't see it, simply because the reasons we just explained. Yeah. Okay. And step 4, again, we talked about this before. So when we have Y capacitor connected in this fashion, it should guide the common mode current back to the noise source. So in this case, we put 2 Y capacitor between the live and the ground, and neutral and the ground, basically. Yeah. And what we see is it didn't bring any improvement. Okay, still hasn't got any improvement, but it doesn't make emission worse. It doesn't make it worse. So, and I think the reason, I put in the reason here. So as you can see, this is really what we wanted to have, right? This circuit is very similar to the circuit we showed you earlier on with that ST design. You wanted to put the common mode choke somewhere here. And
on DC side.
Yeah, on the DC side, perhaps. And then the common mode choke with the capacitor will have LC filter effect. Yeah. But because of the layout, I cannot put a common mode choke on the PCB. It's simply too big. If you put a common mode choke here, it will basically block them, basically.
Block or cancel?
So you block. The canceling is canceling differential noise. So the differential signal is cancelled, but for common mode, it's like a door, basically. I'm blocking you, basically.
It's high impedance or what?
It's a high impedance for common mode current. Yes. So so as I said, we have, the layout is already there. So the best we can try is we have the Y capacitor, but we put a common mode choke on the AC side. It's not ideal, but it's the one way of doing it. So you can see I have the Y cap here and I have a common mode choke here. And I'll show the result. So this is the result. Again, here, the blue trace is where we have the well, basically the green trace is the new result. So you can see now the values is below 17 dB microvolts in some cases. So you can see if this is the 17 dB microvolts line, and the green trace basically they stay quite close to the 17 dB microvolts line. So again, I think another 10 dB reduction. Because we started at 47 or 57, let's go here. Yeah, so we started at 47. So now we're almost 17. So altogether, through the steps, we bring down 30 dB across a very wide frequency range. Yeah, so each step basically brings down 10 dB, and that's what we hoped. As we discussed early on, I said each step we bring down 10 dB, then hopefully 3 or 4 steps we bring down 30 dB. Yeah, so now we have a design that I think at this stage is good enough. You know, of course it's not perfect, but based on their layout and their really bad design, and I think at this stage applying the methods we applied, including adding Y-cap between the primary side and the secondary side, adding a shield on the transformer, adding some Y-capacitors on the AC line. Altogether, we are in a stage that we are happy, basically. And the final step is I can pack everything up in the original little plastic. And yeah, I mentioned something here. Basically, is the beauty of EMC engineering, in my opinion, is you can fix some problems and then you can still use the same box, let's say, because everyone can buy a big heavy filter, you know, like this one, and then put it and it works. But that's not fun. You know, the fun part is to solve the problem as the noise source and pack it up still in an original form.
Not stopping the noise, but stopping the source of the noise.
Yes, yes. And yeah, then we should do some moment of truth test, the final test.
Wow.
So that's the difference. Now we bring back the original setup where we use the antenna, right? Because all the fix we're using a TEM cell. But now we have this small antenna. We pointed it exactly the same way. And you can see that's before and that's after. We're talking about sometimes 40 dB reduction, 40 dB reduction. Yeah. Yeah.
And I think we need to say that the setup for the second measurement, it is exactly same as for the first one. That's why you had all the tape markers and pictures and everything, so you could make it exactly same.
Yes. So so now let's go back to the same setup again, but let's have a look at what's the performance now. Yeah. So now we don't see any spikes and the radio performance okay, you know. So I'm thinking, okay, that's a job done for the radiated emission.
Well done.
I'm currently working on a course specifically for EMC design engineers. And the course will be basically theory-based, but then supported by simulation and real-life case studies. And I believe this approach is the best for engineers to gain the maximum of EMC knowledge. So if you're interested in my course, please drop me an email, which you can find on my website. It's min.zhang@mac1design.co.uk. And we'll let you know the first time when the course is out. Thank you.
And that's everything for today's video. I would like to say thank you so much to Min, because you know, it was a lot of work to prepare all the materials for this video. So thank you so much. And if you have any questions, leave comments. If you would like to let me know what you think about this video, leave comments. If you have any ideas for future videos, you can guess. Leave comments. If you like this video, don't forget press like button. If you would like to see my future videos, don't forget to subscribe. I would like to thank you very much for watching and see you next time. Bye.